Hello and welcome back to Crystallography for everyone. In this video, we are going to look at some more examples of how we determine Miller indices of crystal planes. In the last video, we saw the 100 plane so that we no longer had to describe the front face of our crystal in fairly primitive terms. So we found out that this plane is the 100 plane. But what about the other faces of the crystal? We'll start off a little easier. So what about the top face of the crystal? Same way we don't want to call the 100 plane the front face, we don't want to call this plane the top face. So we can use the same exact procedure as before, except for this time our plane does not intersect x or y instead of y and z. So we call the intercept for x infinity, the intercept for y infinity, and then we are defining this intercept for z as 1. We can take reciprocals again the same way and get the x, y, and z values as 0, 0, and 1. And then again directly get the Miller index 0, 0, 1. So now the top face is the 0, 0, 1 plane. Now we have a good way of describing the front and top faces 1, 0, 0 and 0, 0, 1. We can do the same for the right face. I'll draw in another crystal plane. So we're looking at this right face of the crystal. And I'll repeat the same exact procedure as before, except for we're intercepting the y-axis this time. So we get infinity, 1, and infinity. Repeat the procedure. We get 0, 1, 0. And I think you can see the trend here. This plane, this right face, as we would call it before, is the 0, 1, 0 plane. Now we have the three faces of the crystal here all defined. We have the 1, 0, 0 plane, the 0, 0, 1 plane, and the 0, 1, 0 plane. You might be wondering, what about the other planes? What if we look at, I think I'll do this face. What if we look at this face of the crystal? We saw that the face opposite of it is the 0, 1, 0 plane. But this plane intercepts at what we're calling y equals 0. Let's just try following our procedure as before and see what happens. We intercept x at infinity. We intercept z at infinity, just as our conventions say. Sorry, I wrote that in the wrong place. Intercept z at infinity and y at 0. So we can take reciprocals again. We get 0 for x and z. for y, we get 1 over 0. And you might have learned in previous math classes, dividing by 0 is really bad. If you try and put it into your calculator, it's going to tell you this is undefined. This is not a number. In fact, we would usually call this number infinity. And infinities are hard to deal with. We can divide by infinity, but when we can't really have infinity in a Miller index. It just doesn't work. So there's another convention that we use to deal with this infinity. And this can be a bit of a tricky point, but I think if you see some examples and play around with it a bit, it is not so hard. What we're going to do is change our origin. We have multiple choices of what we can do to change our origin. The main goal is to make it so that this point, which we're calling 0, will actually be negative. In this case, we only have to change our origin in the y direction. What we're going to do is not going to affect the x or z directions, but in some cases it might. We could change our origin to this point. We could change our origin to this point, or this one, or this one. And if we were to do that, let's just see, I could roughly draw another cube here. I think I'm going to get in my own way a little bit. You can see how there would be a cube here, I think. So now we would call this point over here y equals 1. This is y equals 0. And the point we were looking at before is now y equals minus 1. Let's try our procedure again with our origin here. The same as before, we have x and z at infinity, and now y is minus 1. We can take reciprocals, get 0 minus 1 and 0, and directly get our Miller indices from there. So we would call this plane the 0, 1 bar 0 plane. If you recall, we denote minus values, negative values in the index as bar. And even though we changed our origin, this is still okay. So we could we could place our origin back to where we started, and this plane would still be the 0, 1 bar 0 plane, and then this plane would still be the 0, 1, 0 plane. And we could do this for any of the other faces of the crystal. For this bottom face, we would have 0, 0, 1 bar. And for this back face, we would have 1 bar 0, 0. At this point, we have quantified every single plane on or at least the faces of this crystal. It might be a little confusing why this would be negative or a barred value, but I think playing around with it a bit can really help. And it's just a little strange thing about crystallography, but it is definitely more efficient than calling this the left face or the back face or bottom face, especially when we get to more complicated crystals. In the next video, I'm going to go over even more Miller index examples because I believe it's really important to see a lot of these, as many as possible. And we're going to start looking at crystal planes inside of the unit cell, not just the faces. I hope to see you there.